geometric fluctuations in general relativity today. Let's work on how they work.
Okay, so today I understand that I have 90 minutes, so I'll try to be more. Is this just for the room or for taping? Okay, working. Okay, so what I'm going to do in the talk today, so it's actually quite independent of yesterday's talk. Some ideas involving minimal surfaces and mean curvature will come up in part 2 of the talk. In particular, there's a conjecture that will involve some ideas of that type. But what I'm going to do in the talk is I'm going to begin just by describing the Einstein equations and the initial value problem. Okay, so the Einstein equations, a number of the equations that are the general relativity is the theory that unifies special relativity and gravity. Right? So Newtonian gravity historically was not compatible with special relativity. And so the theory that combines those two is general relativity. And so it's a space-time theory, it's a dynamics theory. So I'm going to describe the Einstein equations and the initial value problem. And then in part 2, I'm going to talk about aspects of initial data for the Einstein equations, which are related to several important aspects. One of them being singularity formation, and also things related to gravitational mass and momentum. And then in part 3, so at the end of part 2, I'll pose a specific question. And in part 3, I'm going to describe a very recent theorem which partially answers the question. And so in the end, I'll talk about some very recent work. Okay, so let me begin. So the mathematical model we'll consider is a four-dimensional space-time, which will be a smooth four-dimensional manifold. And then the gravitational field in general relativity is described by a Lorentz signature metric on the manifold. And what that means is that if I take a point in the tangent space, then I can find a Lorentz basis. In other words, I can choose a basis for the tangent space so that the vector E0 has square length -1. So if I take E0 and product E0, I get -1. They're all orthogonal, and the other three have square length +1. Okay, and so the basic model for Lorentz manifolds is the Minkowski space, and so at the tangent space level, so on each tangent space, the manifold just looks like Minkowski space. And actually, later in the talk, I'm going to replace 4 by n+1. So I'm going to actually work in level dimensions. So if we consider the Minkowski space, which is just Rn+1, and if I just call x0 up to xn, the standard coordinates, then the Lorentz inner product on that space, which is linearly isomorphic to the one on each tangent space of the manifold, is just given by, so we can write it in terms of brackets, v and w. So if we take two vectors and express them in terms of the standard basis, then the vectors have components v0 up to vn. And so the v0 component comes with a minus sign, so it's v0 w0, and that's the sum. Okay, and so that's the basic linear Lorentz model. And so on a space-time, on each tangent space, you have you have a picture like that in a suitable basis. Of course, you don't have such a picture sort of locally from point to point, and that's one of the key things. And so the Lorentz metrics actually have a much richer geometry than Riemannian metrics. So Lorentz inner products have a much richer structure than positive definite inner products. Well, partly because there are different types of vectors in Minkowski space or in a Lorentz manifold. So we take a vector, we can divide them into three types. We can take the vectors which have positive inner product themselves. Those are called space-like vectors. And so those are vectors that point outside the electron. So in this picture, the null vectors, which separate the two, form a cone, co-dimension one cone, and a space-like vector would be a vector here. So those are called space-like. And the time-like vectors are the vectors that point inside, either forward or backward. These vectors are time-like. These have negative. Where length and vectors on the boundary are called null vectors. Okay, so in special relativity, physical signals or observers always travel along curves that have time-like tangent. So that's the statement that in special relativity that nothing moves faster than the speed of light. So this is normalized, so the speed of light is 1. Okay, so physical objects always move in time-like directions. Okay, so that's the basic model, and so the Lorentz metric then at each point defines in the tangent space this electron structure, and then I said here that the simplest Lorentz manifold R4, so generally Rn plus 1. And so it's important to be able to distinguish a general Lorentz manifold from the standard one, the Minkowski space. See the theory of general relativity is coordinate invariant. So I could take, if I change coordinates on the Minkowski space, I could get a very complicated looking Lorentz metric. The metric coefficients, the inner products of the coordinate vectors could be very complicated. And so it might happen that your Lorentz manifold is really equivalent by a diffeomorphism to Minkowski space. And so we have to understand when that's true and when they're equivalent. And actually that problem was solved around 1850 by Riemann. He constructed the local invariant which distinguishes a general Lorentz metric from the flat one. So he asked the question, given a general metric in coordinates, so that in coordinates it would just be, so if I take the general Lorentz metric and I choose coordinates, say x 0, so when I x n, then the metric is defined by a matrix of functions. So the functions are g, a, d, which are the inner products of the coordinate vectors, b, x, a, b, x, b. And at each point, that's just a non-degenerate matrix, and of course it varies from point to point as a function of x. And so you have to ask the question, is it possible to change coordinates to make this thing the standard Lorentz metric? So that would mean that, so the standard one is the one here. So in terms of standard basis, it's just it has coefficients -1, +1, +1. Okay, and so the invariant, the local invariant, which distinguishes the general Lorentz metric from the standard one, from the Minkowski space, is called the Riemann curvature tensor. Okay, it's a fairly complicated expression. It's a difficult calculation that Riemann did in order to solve that problem. And the point is it vanishes if and only if, after a change of coordinates, the metric becomes the Minkowski metric. So that's called the Riemann curvature tensor. And so I'm not actually going to try to describe the Riemann curvature tensor. When you've had a course in Riemannian geometry, you already know it. And it takes a while to develop that fully. But I'm going to try to convince you that the part of the Riemann curvature tensor that comes into the Einstein equation is really a lot simpler, and it can be described in a fairly reasonable way. And so I won't go through the physical development of all of this, but in the end, the equation that determines the dynamics of the gravitational field and the coupling with the matter fields is this set of equations. These are called the Einstein equations. So the Ricci tensor there is just actually a part of the Riemann curvature tensor. It's gotten by a trace of the Riemann curvature, so by adding some components together. And so it doesn't contain all of the information that the Riemann curvature tensor contains. So the left-hand side here is a geometric coordinate-free expression involving the metric. So the first term is called the Ricci curvature, and I'll explain in a minute what it means from a geometric point of view. And the function r, that's just the function. It's just the trace of the Ricci tensor. So it's the trace with respect to g. So the Ricci tensor is a symmetric quadratic form. So if I write it in a basis, then it's RAB. That's a symmetric matrix. And then I can take its trace using the metric. So I take the inverse and I contract the sum. So this is R. So that's called the scalar curvature. Okay, and so the left-hand side is called the Einstein tensor, so that's the Ricci minus 1/2, the scalar times the metric g. So it's at each point is a symmetric matrix of it's a symmetric n plus 1 by n plus 1 matrix. And the right-hand side is a symmetric tensor which is constructed from the matter fields. Okay, so there may be matter fields present, and I'm not going to talk about specific matter fields here, but in a certain sense, the right-hand side will play some role, as I'll explain in a bit. So this can be computed. There are prescriptions for computing this is called the stress energy tensor, and it contains the information such as mass density and momentum density. So it tells you how the matter fields are moving, how the matter moves in the space-time. And as I say, there's a prescription for calculating it from for example, if the matter equations come from the variational principle of Lagrangian, then there's a prescription for computing stress energy tensor. But in some cases, it requires, to calculate it requires a bit of sort of ad hoc discussion, physical discussion. But as I say, the specific matter fields won't play a role. Just some general features which I'll describe. Okay, and so an important special case here is when there are no matter fields present. So in that case, the right-hand side is 0. And so what happens is then automatically the scalar curvature is 0, which you can see by taking the trace. So this equation, I have RAB minus 1/2 R GAB equals 0. Then I can just take the trace of the equation GAB, and then on the first term I get the scalar curvature, and the second term I get minus. So the trace of GAB upper or lower is the dimension of the manifold, which is 4 or n plus 1. So in the 4-dimensional case, this would be 2 times R, and it's minus R. So in particular, the equation simplifies somewhat in the vacuum case. So that's called the vacuum Einstein equation. Okay, so it illustrates an important feature of the of general relativity, and that is that you think of matter, the presence of matter, as inducing space-time curvature. Right? So that's the way, if you read the scientific Americans on general relativity, that's what they'll say. But on the other hand, you don't really need any matter to have very non-trivial gravitational field. And so the reason for that is because the gravitational field is determined by initial conditions. And so in the vacuum case, so if you have non-trivial initial conditions at an earlier time, then the vacuum Einstein equations will evolve in a non-trivial way from those. So you can think of electromagnetism, right? So you might have a source that creates an electromagnetic field, but if you move away from the source, it's just traveling freely through space. Okay, and the same idea is true for the Einstein equations. So the vacuum Einstein equations are in fact where most of the mathematical theory is being done. Of course, when you really do physical calculations, you have to consider specific matter fields. But I'm going to present sort of more of the mathematical side of it here. Okay, and so this is the vacuum. These are the vacuum Einstein equations. Okay, and so how do you determine solutions of the Einstein equations? Well, actually, historically, a lot of people just look for solutions which have specific symmetry and look for explicit solutions, okay? So we're not going to go that way, although some of the explicit solutions will play an important role. We're going to look at sort of the general theory. And so from a general point of view, a solution is determined by initial data. So this is an evolution equation. It's actually a system of wave equations. And the initial data is given on a codimension 1, a hypersurface. So it would be a three-dimensional submanifold of the eventual space-time. So the idea is you start with some three-dimensional manifold with some initial conditions, and then you evolve at least locally a four-dimensional manifold from that. And that four-dimensional manifold will satisfy the Einstein equations, the vacuum equations, the ones with matter, depending on how you set it up. But just think the vacuum equations. Okay, and so like wave equations do, the Einstein equations satisfy causality. That means if you want to determine the value of the gravitational field at a point P to the future of the initial surface, then that value depends only on the data in the past at that point. So if I take a point, then I can look at its past. So I look at all time-like and null past-directed curves, and then I can look at where that intersects the initial data. And in fact, only the data in there can affect the value of the gravitational field at that point. So unlike the Ricci flow or heat equations, which are, where global aspects of the initial data affect points everywhere, this is a wave equation, so it can be localized in the sense that the solution really only depends on what happens in the past of the point under consideration. Okay, and this M will be a space-like hypersurface. What that means is that at every point of M, the tangent space intersects the light cone only at the origin. Okay, and so we have this picture here. So using the fact that we can classify vectors as being space-like, time-like, or null, we can similarly look at hyperplanes. We can look at 3 planes or n planes in this picture, and a space-like n plane would be one that intersects the light cone only at one point. And the property that plane has, of course, is that it doesn't contain any time-like or null vectors. So that means if I take the inner product, Lorentz inner product, and restrict it to that plane, I get a positive definite inner product. And so at each point, I have the restricted metric is positive definite, and so the submanifold M is actually a Riemannian manifold. It inherits a Riemannian metric from the space-time metric. By the way, feel free to ask questions. I'd be happy to try to explain it better. It's a little bit, when you talk about the subject, it's a little bit hard because there's a lot of introductory stuff to say. And so I can't say everything, but on the other hand, I'm going to give them the flavors so that people have an idea how the theory works. Okay, and so as I was saying, the gravitational field evolves from initial data, and so you think of it as being like a wave equation. Well, if you think of the wave equation, then the initial data for that is a second-order hyperbolic equation. So the initial data is the initial position and the initial velocity. Right? And so the same thing is true here, except now everything is geometric. It's all coordinate free. So the initial data for the Einstein equations, think of the vacuum equations first, are the Riemannian metric, that is the induced metric G. So that's a given Riemannian metric on M, on the initial manifold. And then the time derivative, the role of the time derivative is played by the second fundamental form, P. And so these play the role of the initial position and velocity. Let me explain why. Okay, so actually, first of all, if you think about this, you should say, well, that sounds a little odd, because how many Einstein equations are there? Well, let's say we're in 4 dimensions. It's a 4x4 system of equations, and it's symmetric. So there are 10 equations, 10 Einstein equations. On the other hand, the restricted metric, that is the induced metric, is only a 3x3 matrix. So there are only 6 components for that, right? And so we're missing 4 components for the initial data. And that aspect of the Einstein equations is related to the coordinate invariance. If we were dealing with just an ordinary second-order wave equation, we would have the same number of initial conditions as there are equations, both position and velocity. Okay, so here it's a little different. There's a bit of a twist there. And so the initial data is only consists of locally 6 functions, which are the reduced metric. And the second fundamental form is as I said, plays the role of the initial velocity. Let me explain that a bit. Okay, because I talked yesterday about the second fundamental form, and I described it in terms of normal curvatures of curves on the surface. And so that is a correct description. But there's another way of looking at it in terms of a sort of foliation or a family of surfaces. Let me just describe that. So actually, when you evolve the Einstein equations, when you solve the equations, there's not a canonical time function, which is, so you think of the initial data being at time 0, but then there's not a canonical time function that's defined. You remember it's coordinate invariant, so you can change time functions. And so if we take the simplest case where the level surfaces, so let's think of this is the initial surface, m, which is, let's call it m0, and then if we look at our time, so x naught is abbreviated t, and if we take surfaces which are parallel locally, so this is mp, and so in other words, we think of, we can always foliate a space. If I take a hypersurface, I can foliate it where one of the coordinates is the distance to the hypersurface. Okay? And I can do that, and I can do that also in the Lorentz case. Right? So the distance, these are separated at constant distance in the sense of time-like curve. So a time-like curve also has a length. It's called proper time. Right? So the MTs, so if these are equally spaced, then what that means is that the vector ddt has length -1, and it's orthogonal to the vectors it's orthogonal to the tangent vector. Well, it's orthogonal because the MTs are the level sets of this. So ddt is orthogonal to. So if I choose coordinates where the x's are tangential, so I have x naught, and then I choose coordinates of these guys, which are x1 up to x3, then the inner products of ddt with the dx's are 0. Those are so they're orthogonal. And then when I do that, and when I think of differentiating, so if I take the induced metric, so if I take gij, which is the inner product of ddxi with ddxj, and I differentiate that in time, I take ddt of it. Then what do I get? Well, you write it here on the screen. So I take ddt of that. Well, then I can apply the Leibniz rule. So I take the derivative of ddxi with respect to ddt. So that's actually the covariant derivative. Use the Lipschitz connection there. But when I do that, I get the two terms. I get del ddt ddxi ddxj. And then plus the other term. Yeah. But on the other hand, these covariant derivatives, because these are coordinates, actually commute. I can do this in either order. And when I differentiate ddt, so ddt is the unit normal to this hypersurface. When I differentiate it tangentially to the hypersurface and take a tangential component, I get the second fundamental form. Okay, and in fact, it's symmetric. So this expression is actually equal to 2 times the second fundamental form. It's 2 times what I call Pij, the second fundamental form. Okay, and that's why the second fundamental form is the time derivative of the metric. And so it's a sort of a general geometric calculation. Actually, you can. I usually often give it as an exercise for surfaces in R3. You can also think of the second fundamental form of a surface as the rate of change of the first fundamental form for a parallel family of surfaces, and that's this calculation. So okay, so that's those are the initial position and velocity. And then there's a very, very important aspect of the Einstein equations, also again, which is related to the coordinate invariance, and that is that of the 10 equations, 4 of them actually are non-dynamical equations. So they're equations that can be written entirely in terms of the initial data, in terms of G and the induced metric, the given metric, and the second fundamental form. So the initial data for the Einstein equations then would be, if I were doing it in 4 dimensions, would be a three-dimensional manifold with a Riemannian metric and a second fundamental form. This is called an initial data set. But the problem is, so if you think of wave equations, then you can specify arbitrary initial data, initial positions and velocity. That's not true for the Einstein equations. So it turns out that G and P themselves satisfy a system of 4 PDEs, which are called the constraint equations. And they represent 4 of the Einstein equations. So I'm in the vacuum case. So they represent the Einstein equations which have, if I call this vector E0, normal, so the zero A set of equations for A equals 3. 0 A equation. So in other words, RAB, R0A. Well, let's just take the vacuum case. These are R0A and 0. So those 4 equations actually can be written in terms of initial data. And actually, if you know a little bit about the Maxwell equations, there's a similar thing that happens for the Maxwell equations, right? When you do electromagnetism, the initial data is the electric field and the magnetic field at time 0. On the other hand, they're not freely specified. If you're doing the free Maxwell equations, they have to be divergence free. And so this constraint equations for relativity are sort of the analog of that, the constraints for the Maxwell equations. And so they're just a little more complicated. Of course, they're nonlinear equations, whereas the Maxwell ones are linear. And so the equations actually just come from purely geometric equations. They're the Gauss and Cadazzi equations. So it turns out if you look at the 0A component of these, you can express everything in terms of initial data. So right. You can so the Gauss equation relates the ambient curvature in the tangential directions to the intrinsic curvature in the second fundamental form. And that first equation comes directly from the Gauss equation. It uses the fact that the Ricci tensor of the ambient manifold is 0, and it's really a trace of the ordinary Gauss equation. You think of hypersurfaces in Rn plus 1, or in the Gaussian plus 1 space. And this other set of equations comes from the Cadazzi equations. Remember, the Cadazzi equations involve first derivatives of the second fundamental form. And so this involves first derivatives, but again, it's a trace, reflecting the fact that the Ricci tensor doesn't encode all of the Riemann curvature tensor. Okay, and so this is a set of 4 nonlinear PDEs. So the second, these are actually coupled equations because the del there involves the metric G. So this involves, it's linear, of course, in pi if you fix G, but if you, the coupling term is a nonlinear term. Okay, so this is a system of 4 equations, 4 nonlinear PDEs for the initial data, the G and the P. And so these are called the constraint equations. Okay, and so the initial value problem says that if I take an initial data set that is MGP, and if it satisfies, say, the vacuum constraint equation,